Up to this point, we only know how to calculate the work of a thermodynamics process for two scenarios. The first one, if we know or calculate the internal energy and heat transfer from our conservation of energy equation and kinetic energy and potential energy terms if any, and solve for W, and the second, W equals P delta V, in the cases where the pressure in our process is constant. In this lecture, we'll learn how to calculate work in variable pressure systems. In the Enthalpy and Internal Energy 12-minute lecture video, linked below, we concluded that for constant pressure processes, since the change in internal energy is equal to the heat transfer minus the work done, when neglecting other types of energy, the work is equal to the integral between states of P dV. And we went over how, for these constant pressure processes, that integral results in just P times V2 minus V1, or Pm times V2 minus V1, and how we can even skip this if we're calculating the heat transfer and find the total heat transfer with the enthalpy values H2 minus H1 or mH2 minus H1. But this expression is true for constant pressure or non-constant pressure processes. When pressure varies during a process, we call it a polytropic process, and the expression that allows us to solve for unknown properties of an ideal gas that undergoes a polytropic process is PV to the n equal to a constant. The n variable is known as the polytropic index. Let's see where this equation comes from, and we'll use several of the statements we made in the previous lecture, so make sure to watch that one before watching this. We know that for infinitesimal changes, our energy conservation equation, or first law of thermodynamics, results in delta Q equals to du plus delta W. The heat can be written as mc dt, with C being the specific heat at constant pressure Cp or constant volume Cv, depending on the process and therefore indeterminate for now. And du is equal to mcv dt from the definition of what Cv is. The infinitesimal work is just P dV. We can simplify this equation as mc minus Cv dt equal to P dV. For an ideal gas, PV equals to mRT. The differential form of this equation would be P dV plus V dP equals to mR dt. We can solve for dt and substitute it in the conservation of energy equation. Since the mass term cancels, we can now multiply by R on both sides, then distribute the parentheses, and since in the last lecture we proved that Cp equal to Cv plus R, we can substitute these terms by a Cp. We can now divide by C minus Cv to have a coefficient next to P dV, and also divide all terms by PV. Since the coefficient of C's is constant, we can integrate, with those terms outside the integral, to get the parentheses times natural log of V plus natural log of P equal to a constant. If you remember basic exponentiation and log rules, you might remember the log of a power rule, where y natural log of x is the same as natural log of x to the y. We can therefore write the first term as natural log of v to the parentheses. And you might also recall the product rule, where natural log of x plus natural log of y is equal to natural log of xy. This means that the left-hand side is the natural log of pv to the parentheses, and therefore this is equal to a constant. The parenthesis is what we call the constant n, the polytropic index, and therefore for a polytropic process of an ideal gas, PV to the n is constant. This also means that P1V1 to the n is equal to P2V2 to the n equal to P3V3 to the n, etc. We'll take a look at other cases in just a second, but what happens if we try to apply this equation to an isobaric process? An isobaric process, or in other words, a process at constant pressure, means that our general specific heat C is Cp. This would mean that n is equal to 0. What about an adiabatic process, meaning that no heat comes in or out? In this case, since dq is 0 and temperature changes can still occur, we would say that C is equal to 0. Substituting this 0, we see that n becomes Cp over Cv, or K, the specific heat ratio that we established in the previous lecture. For adiabatic processes, this equation becomes Pv to the K equals constant. For an isochoric process, constant volume, we would have the general C be Cv, the specific heat at constant volume. In this case, the denominator would approach 0 and therefore n would approach infinity. This is not very useful in terms of solving for values, but it does allow us to plot these processes in a PV diagram, where P is on the y-axis, V on the x-axis, and for n equal to 0, isobaric process, the slope is 0. N equals infinity is an infinite slope or a vertical line, and an adiabatic process has a logarithmic slope equal to k. The first two make sense. N equal to 0 is isobaric, meaning that the pressure never changes, and n equal to infinity is isochoric, meaning that the volume is always the same. We'll look at an isothermal process in just a second. Just remember that depending on the path from state 1 to state 2, the shape of this curve can be described by different values of n. The reason we use this relationship is because we need to know P in terms of V so that we can integrate P dV and calculate work. Substituting P in terms of V in the integral looks like this, or with the V in the numerator and the constant outside of the integral, we get V to the minus n. After integrating this expression, we find an equation for W in terms of the constant C. And since the constant is P1V1 to the n or P2V2 to the n, we can distribute it in our expression and substitute it for P2V2 to the n in the first term and P1V1 to the n in the second term, and use the product exponentiation rule to find the expression for work of a polytropic process in terms of P and V only. This expression is only true for n different than 1, and not because we would run into some mathematical issues dividing by 0, but because if n had been 1 from the beginning, the integral would have been the natural log of v2 over v1 times c, in this case pv. This is the expression for work of a polytropic process when n is equal to 1. And notice that P and V can be that for any state, P1V1, P2V2, P3V3, since the constant is the same for any state. And what does it mean that n is equal to 1? Well, if P1V1 is equal to P2V2, from our ideal gas equation, this is only true if the right-hand side of the P times V equation is constant. The right-hand side is R bar T1 for the first one, and R bar T2 for the second one. If these two are equal, it means that T1 and T2 are the same. Therefore, the big conclusion here is that when an isotropic index n is equal to 1, the process is an isothermal process, or a process where the temperature is kept constant. Let's make use of these expressions with a simple example, and if you want to see more complex examples, make sure to check out the videos for this topic in the description below. 2 kilograms of air at 130 kilopascals and 22 degrees Celsius is contained within a piston cylinder. It is compressed to a final pressure of 550 kilopascals. During compression, heat is transferred from the air and the temperature remains constant. Determine the work input required using a molecular mass for air of 28.97 kilograms per kilomole. As always, pause here and try to solve this problem before watching the solution up next. To solve for the work, we know we have two options we derived today. One for when the polytropic index is not 1, and one for when the index is in fact 1. And since we're being told that the temperature remains constant, meaning an isothermal process, we know n is equal to 1. We have P1, P2, and T1, and again we're trying to find the work, which from these equations we see that we first need V1 and V2. To find V1 first, we can multiply the specific volume V1 times the given mass, and to find V1, we use the ideal gas equation. Remembering that R is R bar over M, with M for air, and that temperature has to be input in Kelvin, not Celsius, we substitute the pressure to find the specific volume of state 1 in cubic meters per kilogram. And like I said, since we're given the mass, we find V1. Now, since we do know that n equals to 1, then P1V1 is equal to P2V2, and therefore V2 is equal to P1V1 over P2. With this, we can find the volume at state 2. And finally, we use the expression for work that we derived today, and it doesn't matter if we use P1V1 or P2V2 here. Since n is equal to 1, they are both the same. This negative value we get for work is consistent with what we know about heat and work. Since this is a compression process, we need to put work into the system to compress it, and our convention was that work in must be negative. If you want to check out other examples on this topic where we use the other expression we derived here today, or the other lectures of the thermodynamics course and lectures of other engineering courses, make sure to check out the links in the description below. Thanks for watching.